We're going to start this video about wave characteristics. Okay, and we're going to just talk about some different properties of some different types of waves. One of the first things we need to talk about is something called intensity. And basically, this is defined as the amount. I'm just going to put AMT, amount of energy per unit area per unit time that flows through an area. So it's like a flow. It's the amount of energy per unit area per unit time that flows through an area. But if you look at this, it's essentially energy per area per time, which is just energy per area times time. And this energy per time here is power. So the other way you can look at this is it's the amount of power through a certain area through unit time. So basically, if we took and made like some sort of some sort of plane here like this, and then we had power or energy flowing through it like this, then we measured the amount of energy going through this area right here through in a certain amount of time. That would be our intensity here. For waves, this intensity, which we'll use the capital letter I for intensity, is proportional to the amplitude of the wave squared. So that's important. Intensity is proportional to amplitude of your wave squared. So the taller your wave is, obviously, if you think about this little wave here isn't going to transmit much energy compared to like a huge giant amplitude of a wave, right? There's going to be a lot more in there. If you were shaking a string in order to make waves on it, this little shaking wouldn't be a lot of energy, but if you shook it really big and fast, that'd be a lot more energy in it, and it would give it a larger amplitude. Okay, so that's an important relationship to remember. You don't have to know everything else that goes with it. Just know that when it comes to waves, intensity is proportional to the amplitude squared, and that's actually a pretty useful relationship. The other relationship, if you're talking about spherical situations, which if you think about this as a wave were to go out in all directions, like say we had a sound, you clapped or something and it went out in all directions, that compression wave went out in all directions, well, what would happen to the intensity of it as you got further and further away? Well, it's very similar to our gravitation laws and stuff like that. As it goes out, we have this spherical symmetry, so the amount of power that was in it, so say we had a little, we started with it and it was really intense right here, but as you get further and further away, sorry, that was supposed to be a circle, as you get further and further and further away, the amount of energy that you had all right here gets spread out, and so it spreads out and it gets weaker and weaker as you go further and further out, and it weakens as the surface area does, 4 pi r squared. So essentially what that means is that energy spreads out over a larger and larger sphere. Over the surface of a sphere is that intensity is proportional to 1 over r squared, because this is a constant, so we don't have to worry about it in the proportion, but it's proportional to 1 over the distance squared from the source of the wave. So, excuse me, if this is the source of the wave, then whatever r happens to be, the further you are away from it, the weaker it will get. All right, now we need a way to kind of represent waves, and I kind of just did almost right here as a sound wave went out, but what we're going to do is talk about how do we draw wave fronts, what they're called, wave fronts. And so the basic idea is to draw lines that represent a crest of a wave. So these are wave fronts. They're the lines equal the crests of waves. So if, for example, I dropped a stone into a pond, what would you see? You'd see ripples, kind of look something like this. You'd see these ripples going out, right? Ripples, and it would be these concentric circles as we went out. And these lines, what we do is say we drew a line on a crest everywhere. So this would be a crest, and this would be a crest, and in between would be a trough. And then you could look at it and say, all right, well, what's the wavelength? The length would be between the two crests. That would be lambda here in this case. All right? And then as you got further and further away from this, of course, as a circle gets bigger and bigger, it gets flatter and flatter. So, if we kept going out further and further and further, this just gets flatter and flatter and flatter and flatter. And eventually, these wave fronts that look like circles here start to look like just, I'll start different, they just start to look like parallel lines. And so, we can put like an or there. So, or we get this kind of parallel wave fronts that look like this that aren't circular anymore because you're far enough away, or it was just made in a different way, so it wasn't spherical to begin with. Kind of like one of those wave pools at a water park. They have all those waves coming in like that that are plane waves, they're called. These are spherical waves, these are plane waves. They can be transverse or longitudinal. It just has to do with the shape of the wavefront. So this would be crest, and again, the length between them would be the wavelength. Now, drawing this kind of thing can be kind of a pain. Say, for example, I have light, which is a wave, we know, and I have it going through a lens. So let's say I had a lens. We'll make the lens green or something. So I have a lens here, and lenses focus these waves. So what would happen is I'd say I had a source here, and it emits this wave out, and this wave's going to go out, and then it's going to hit this. And the part that hits this, right, is going to get focused down. And so it's going to start focusing down like this, and then it's going to cross and start getting bigger again like that. Bigger, spreading out more and more and more. And this is how you would represent what happens with a lens focusing light in a situation like this. Well, this is kind of a pain to draw. I don't like having to draw that. So what we can do is instead start to draw what are called rays. These are rays. And what this is will be lines that show the direction of energy propagation. So it's the direction the energy goes in, propagation, right? The energy propagation direction. And so if we were looking here, if I drop a stone in here and the waves start traveling outward, well, what direction are the waves going? Well, they're going outward, like that. That's the direction the energy is going. It's going away from where the stone was dropped in the water, or where the speaker made the sound, or somebody clapped or something like that. So we could represent it with something like that. And you'll notice that these ray lines are perpendicular to the wave fronts wherever they're crossing them. And the same thing over here. We can draw these rays in that would go like this, and they show us the direction that the waves are traveling, that the energy is propagating with the waves. And then if you were drawing something like this, the picture becomes much simpler. I don't want to go too far down, but let's say we have our lens here again, right? Well, instead of drawing all of that in, right, I can just draw in the rays. Here comes the light out this way, here's the direction of propagation, and then it focuses and does something like this, right? It crisscrosses. So we end up with drawing a picture that's a lot simpler just by drawing this ray diagram like this rather than that. I mean, I guess you can draw both in, but this is the direction that the light's going in, right? And of course I'm perpendicularly crossing all these wave fronts everywhere, right? Just kind of drawing it in on that one already, but drawing it just the ray diagrams in would be a lot simpler, right? And this would be just one going straight through, but it'd look something like that. Okay? And so that's ray diagrams. Takes a little practice, just work on those. And what you'll start to do is just draw, oh, here comes the sound. You won't have to draw the wave fronts into just the rays. So that would be like drawing this picture, and you'd know that if I looked at this would just be a bunch of concentric circular type waves, and if I looked at this picture here, if I saw the ray picture like this, I'd know that the waves were perpendicular to those rays like that, and it was a plane wave like what we had up here. Okay, the next thing to talk about as far as wave characteristics goes is wave interference. Okay, so interference of waves. So this is basically the question of what happens when waves overlap, when they run into each other. What's going to happen when they get on top of each other? And to answer that, what we need is something called the law of superposition, or the superposition principle. One of the two. But basically it's superposition. And what that means is it superimposes one wave on top of the other. It's a fancy way of saying you add them up like vectors. You do the vector sum of the overlapping waves, or the parts of the waves that are overlapping. Okay, it's just a vector sum, and we can either have this can either make the wave bigger, in which case it's called constructive interference, or it can make the wave smaller, in which case it's called destructive interference. And I'll show you an example of both of these. So let's say we had a wave crest headed this way, and another wave crest, a smaller one, headed this way. Well, what would happen as they ran into each other? Well, if we draw them both, again, trying to draw it, there's that first one going that way, and then they're slightly overlapped. Here's the shorter one like that. Well, what would happen is you would go in and you would want to add up wherever they overlapped. So from here, before that, they're not overlapping, so it's not going to change that wave at all. That was supposed to be on top of that. So that doesn't change. But here, this wave has a little height to it. So what's going to happen? It's going to add a little height to this one, so it's going to start to get a little taller. And then as you come over here, it's a little taller, and this one gets a little shorter. So you take this height here, and you take this little height here, and you add them up, right? So I'm taking this little bit here, and I'm putting it right on top. So it's going to make it like that tall. And then in the middle, they're both the same height, so I'm just going to make it that height and double it. And then here, you take this little bit and add it on top of that wave, and it puts you like here. And so basically, and then over here, it's just a little bit higher, and then it goes back to being. So you go just like point by point, and you add these waves up. And what happens is you get like this little kind of dippy thing, but you get a wave. I'm not sure I'm drawing that absolutely perfectly, but they start to add up. And so this green wave would be the wave that you would be seeing. And then when they're right on top of each other, right, the taller wave and then the shorter wave right there. Sorry, that's not very well, but basically, if this was like 2 high and this was 1 high, what would happen is you'd get something that was 3 high. Okay, and it'd be wave interference. And then the neat thing is, though, this one was going that way, that one's going this way, and again, still going this way and that way, is after they finish interfering, they go back to being just exactly what they were before. This one going off this way and this one going off this way, as though nothing ever actually happened. So the only time they have an effect on each other is when they're on top of each other, and as soon as they're done interfering, they go back to right what they were. Okay, so this kind of interference was constructive. And again, you just go point by point. It's like adding up 2 positive numbers. I have these things overlapped. Maybe draw a little bigger picture here. So I have this wave, and I have this wave here, and where they're overlapped, like right here, I'd take this height here and add it on to this total height there. So I'm taking this little bit here, and I'm putting it right above it, and I'm adding it on. And so the new wave height at that point would be way up here. And then I'd go to the next little point over, and I'd say, all right, take this height here and add it on there, and it's going to put it, like right there or something. And so you'll get that wave interference by doing that. Okay, so let me get rid of that because I didn't want that on there. I just wanted to show you a bigger version of it, but you just go basically point by point, and that'll get you your wave. As long as you're meticulous enough, you can go through and do this. Next, what about this happen? What happens if we have a crest traveling this way, meeting a trough, a dip down there like that? Well, it's the same sort of thing happens. You'll have the crest like that, and then the trough slightly overlapping it here, and what you're going to do is go point by point. So here it's all the same, but as soon as I start to like overlap right here, this now subtracts off from that. It's kind of like I had a mountain of dirt here and I started throwing it in a hole. So this little part here I have to subtract off a little bit, so it starts to go down faster, right? And then same thing here, this subtracts off it, and so what you end up with is something that subtracts off, and then this gets a little higher, and you end up with something like that, where it does something like that, where you end up with that. And then when they finish overlapping, when they're like totally, sorry, not finish overlapping, when they're right on top of each other, you get something that's like, say, if this was 2 and this was -1, it was you get just a smaller wave like that. And then, of course, after they're done interfering, this trough would just be over here going that way, and the bigger crest would just be over here going that way, and they just go on their merry way. And this kind of interference is called destructive interference. And I know I'm not the best drawing it, but I'm trying my best. You could probably look up some pictures of this and see a little better pictures than these green drawings I'm doing. But they interfere. It's kind of like adding positive and negative numbers. This is a positive number, this is a positive number, so it gives you a bigger positive number. Add 2 positive numbers, you get a positive number. Here you have a positive number and a negative number, and you get a smaller positive number. You could get a smaller negative number if, say, this had been the bigger wave and this had been like the smaller wave. Then it would have been just whether or not you get a positive or negative number depends on whether or not the positive number was bigger or the negative number was bigger. But essentially, when they're totally interfering with each other, it's just like adding positive and negative numbers. Crests are positive numbers, troughs are negative numbers. And when they're slightly overlapping, you can't just look at the crest and the trough. You have to go like point by point. So you look at this positive number and this negative number, and you add them up, and that's where it'll end up. And this positive number and this negative number, and you add them up, and that's where the wave will be at that point. Okay? One of the very interesting things about this kind of interference is what happens if you have the same size crest, meaning the same size trough. So if this was like a meter high and this was a meter low, what would happen? Well, when they'd get on top of each other, you would get an interference that would just be flat. There'd be nothing there. So they would cancel each other out. But what would happen after they finished overlapping? So you'd have these 2 waves traveling along. They get on top of each other. They totally cancel each other out, so there's no wave anymore. And then what happens? Does it just totally cancel out and become nothing? No. The same thing that happens above. They suddenly would basically reappear with the trough on this side and the crest on this side, right? So if this was going this way and this was going this way, with the trough going this way and the crest going, they'd basically just reappear. I always thought that was really neat, that they could cancel out. Essentially, it'd look like you had nothing, and then a moment later they'd reappear, and you'd have your 2 waves again going on as though nothing had happened. All right, so kind of keep that in mind. Don't get tricked by that. Your waves can totally cancel out and then still manage to come back. Okay? They go right back to normal after they finish interfering. Okay? This kind of thing is what you have, those noise canceling headsets. Essentially what they have is a little microphone in there. It listens to the sounds that are outside the headphones, like the sound of the airplane or the car or something like that. And then what it does is it creates the same sound again, but with troughs like this. And what it does is it totally cancels it out to this so that you can't hear it, those active noise canceling ones. They basically try to put out a sound that'll cancel out the other sounds and make their wave heights 0 so that you don't hear it. Okay, just a little something extra there. After interference, the next thing we have is polarization. All right, and this is the last thing for this part. Polarization. So if you remember the picture we had of light, it had an electric field that was pointed in one direction, right? And then perpendicular to it, we had an oscillating magnetic field. So you had an electric field and a magnetic field. And yes, we use B to represent magnetic fields if we haven't gotten to that yet. It's called a B field, but a magnetic field and an electric field that are perpendicular to each other. Well, polarization is essentially just looking at how these are oriented. If we make just some random thing of light, like the light coming from the sun or from a light bulb or something like that, well, what happens is these electric fields aren't always lined up with each other. Sometimes the electric field might be pointed this way. So now let's only think about the electric field. Let's not think about the magnetic field. So the electric field might be pointed this way, or this way, or this way. And in fact, that's really what happens, is you get this jumbled up bit of electric fields that are all pointed in different directions, because there's nothing that said all the electric fields must be straight up and down. So you get this kind of mess of it. And what this is basically just regular light. This is non-polarized light. But what if we could come up with a way to actually take light like this and turn it into light where the electric fields were all pointed just straight up and down? Again, we're ignoring this B field now for the moment, the magnetic field. What if we could turn it into light where all the electric fields were pointed in the same directions? If we could do that, this light, this here, this would be polarized light. And the process of polarizing this light, getting polarized light from non-polarized light, is polarization. So we're going to look to see if we can get all the electric fields, all E fields, pointed in the same direction. Okay, all the electric fields pointed in the same direction, just like that. So we'd have all these particles of light, and they'd all be this way, not all jumbled mess like that. So there are two main ways to do this. Two main ways. There's more than this, but as far as this class is concerned, you really only need the two ways. The first way is through reflection. And when non-polarized light reflects off a surface, so let's say we had some surface sitting here like the ground or water or something like this that's sitting horizontal, and we have this light coming in, that's all this non-polarized light, right, headed in like this. And what this light's going to do is it's going to come in like this, and then it's going to bounce off. So kind of drawing in that light ray, just like this. It's going to bounce in. So we have all this non-polarized light like that. But when it reflects and bounces off of a surface, it actually polarizes parallel to that surface. And so it would polarize this light in this direction. Okay? And we're going to make use of that in a minute once we talk about, well, great, what's the point of knowing of this? Well, we can actually take advantage of it doing that kind of polarization here in just a minute once we finish talking about the second way. So the first way was reflection. The second way is through a polarizing filter. So you can use a polarizing filter. And you can look up little videos on these, but essentially what this is imagine like a, well, let's give an example. Let's imagine we had a set of blinds, like the kind of horizontal blinds you have on a window, like this, right? And they're all horizontal blinds. Well, if I threw a bunch of sticks at this, so let's get brown. If I throw a stick at this and the stick is this way, it's not going to get through the blinds. It's going to hit the blinds and get stopped, right? But if I throw a stick that's horizontal like this at the blind, it's going to make it through. It'll be able to fit between there and get through. So if we do a side view of this, it's going to help, but let's say this is our side view of it. Here's our blinds like this, right? Well, all the vertical sticks are going to get hit and they're going to get stopped. But all the like horizontal sticks that are sideways, they're going to make it through. They'll be able to get through. And so if we can make a filter that is like this, that's not really blinds, but down on like on a molecular scale, it has these kind of horizontal lines to it. Well, we could cut out any of the light that is not in the same direction as the polarizing filter. So what you can do is take some sort of polarizing filter. Let's say we had this filter that was like this, right? And it's filtered this way. And what we can do is send, this is my quick little sketch of non-polarized light. It can be sent in, right? And so it can come in this way and then come through the filter. And when it comes through that filter, the light will be polarized in the direction that the filter was, right? And there we can polarize this light. And anything that isn't polarized in the direction of that light won't make it through. Okay, and so that's polarizing using a filter. Now combining these two ideas, we can do a couple of interesting things with it. There's really a lot more than this. The first is we can reduce glare. So if I were to take and put a second filter after this one, so let's say we put another filter here, another polarizing filter, but this time I rotated this filter this way, right? So it wasn't like that. What would happen is all this horizontally polarized light would hit this. There's only horizontally polarized light, and it wouldn't be able to make it through. Which means if I have a horizontally polarizing filter before a vertical polarizing filter, it'll essentially block 100% of the light. It'll block all of it. So no light can make it through like that. And it will stop it. And you can look this up, see videos of it as you rotate this and get them perpendicular. It blocks all the light. It's pretty neat. If they're both turned the same way, you can see through them. If you rotate one of them 90 degrees, suddenly you just can't see through it anymore. It becomes totally black and you can't see it because it blocks it. This blocks all the vertical light, this blocks all the horizontal light, and so no light gets through. So we can kind of take advantage of doing something like this. So you could imagine, say you're out fishing on a boat, and now this plane that the water is reflecting off, say that's the water. Well, if you get up here in your boat and you have sunglasses that has a vertical polarization to them, right? So you get your sunglasses on, right? And you have these sunglasses, and on the lenses you put vertical polarization on them. Well, look at the water bouncing off. The water bouncing off the water is going to be horizontally polarized, and when it comes up to your eye, it's not gonna get through your glasses, which means you won't see any of the reflection or the glare off of the water, like the sunlight beating down that makes the water so shiny. And if you're fishing and that's the water, you might be able to see the little fish swimming around under the water, and it helps you with fishing. If it's not fishing, if you're not fishing and you're out driving, this can cut down glare on the road, like light shining off the road or off of other cars. These vertically polarized lights help cut down a lot of glare, and then you're not having as much light shine into your eyes and you can see better. So this kind of thing is helpful as well for cutting down glare. And they'll do this also as well to cut down reflections. Like say they were filming a movie, put a polarized filter over the lens for the video camera, and now you lessen the chances of seeing a reflection of your video camera or of your movie camera in like a store window or something like that, where the light reflecting off the store windows, you can't see it, and also you can see then through the window, and you're not just seeing a bunch of glares and reflection off the window. Another use of this kind of thing is LCDs. LCDs use polarization to make them visible. So you can use an LCD to actually polarize light. So if we have our video projector here, right? Here's our video projector, whatever it is. You know, it's got the movie going on here. And the video projector is shining this light out, right, onto a screen. And then after it hits the screen, it bounces off to you sitting here watching the movie. The light goes and hits the screen, bounces off, and comes over here and you see it. Well, if we put a little LCD filter in front of this, and what you do is you make every other frame of the movie. One frame is what you want your left eye to see, the next frame is what you want the right eye to see. And then every time it's a frame where you want the left eye to see, it polarizes one way. And every time it's a frame you want the right eye to see, this little screen, this little LCD screen here polarizes it the other way. And so what happens is you then put your glasses on, and I guess I didn't draw this the right way, but you put your sunglasses, your movie theater 3D glasses on now. It used to be red and blue, where one of them is polarized horizontally and the other is polarized vertically. That didn't turn out very well. So here are your glasses. One of them polarized horizontally and one polarized vertically. And so the light that got polarized horizontally through this little filter here, you can see it with this eye, but this eye can't see it. And the light that got polarized vertically, you can see it with this eye, the eye that would be behind this lens, right? But you can't see it with this eye. And so what happens is each eye can only see every other frame. The left eye can only see the frames that are supposed to be from the left eye's view, and the right eye from the right eye's view, and then it gives this illusion of depth, and it looks like a 3D movie. Okay, so you can use this as a modern way to do 3D type movies. Okay, so the last little bit is to talk about this with a little bit of mathematics. So what happens is when you send light through just a single, so light through a single polarizing filter, so a single polarizer, when light gets polarized once, so through a single polarizer, the intensity is cut in half. So it's half. So like I before is equal to 2 times I after, which basically means I after is half what it was before, and it cuts it down. Well, what happens to the intensity if you send it through 2 filters? And these 2 filters don't have to be at exact right angles to each other. What happens if you have a filter that's, this way, and then your next filter, right, your next filter here is, let's put it at an angle, is, at an angle to it. It's not, let me get rid of that. I'm going to draw that a little better. Why didn't that work? Sorry. So let me try that again. Let me grab that, delete it, sorry. There we go. So the next little filter, let's say we rotated it some amount, but not totally 90 degrees. Well, then it's not going to block all the light coming through the second filter, it's only going to block some of it. So as our light comes through, so we have this unpolarized light first, then it gets polarized, and then it goes through the second filter, and it comes on out here. So we're not really interested in over here. Whatever we have here, this intensity, we're more interested in what's the intensity here in the middle. We'll call that I. Then just for completeness sake, this would be 2I. This would be I, right? Here comes the light going this way. What would this intensity over here be? We'll call it I naught for after the second filter. And it turns out it's a pretty simple relationship for calculating that, and it's that I naught is equal to I times the cosine squared of the angle between the 2 polarizers. So if this polarizer is this way and this polarizer is this way, right, then theta is the angle between them. Probably could have drawn that a little better. One's polarized this way and the other's polarized this way at an angle to it, where this angle between the polarizers is the angle theta. So if you wanted to see that over here, you could say this is polarized this way, this is polarized this way. It's that angle theta right in between there. Probably should have picked a color other than yellow, but it's that angle theta between the direction of the polar. So this is polarized this way, this is polarized this way, and so what we're interested in is that angle between them. And that's that cosine. And if you think about it, what is, as we rotate this and it goes to 90 degrees, what's the cosine of 90 degrees? 0. So in that case, no light would be making it through, and as you rotated it back towards 0, toward there being a 0 degree angle between them, cosine would get bigger and bigger and bigger, and if you went to 0 degrees where they were parallel to each other, cosine of theta is 1, so they would just equal each other. They wouldn't block out anymore because a horizontal filter with a horizontal filter or a vertical with vertical is not going to do any extra good for you. Okay, so that's our last big equation we need, called Malus's law. I think that's how you pronounce it, M-A-L-U-S law. Okay, I think that's pretty much everything.